Let's continue our lecture. So this is the calculations related to electrolysis. In the electrolysis of a solution containing nickel to iron, metallic nickel deposits on the cathode using a current of 0.150 ampere for 12.2 minutes. What mass of nickel will form? So you need to calculate the mass of nickel. So the question gives you the current and also the time. So the time here in minutes convert to second. So this is the current. You multiply by the time and you get the charge. So this is the Faraday's constant. And you get the 1 mole of reactant divided by the number of mole electrons. So mole reactants, you times with the molar mass, multiply by molar mass, and you get the mass of nickel. So look at this solution. Number 1, you calculate the charge passing through cell in 12.2 minutes. So this is the columns is equal to the current multiplied by time. So this is the columns 109.8, and then calculate moles of electrons. So number of moles, the columns you divide by the Faraday's constant, 96,500 coulombs, and this is the number of mole. To get the mass, number of mole you times with the RMM, but before that you need to divide by the number of mole electrons. How do you get the 2 here? Look at the nickel, 2 positive, meaning that to get the nickel, so nickel 2 positive here, again 2 electrons, and produce the nickel. So 2 electrons is the number of mole electron. So 2 here, and multiply by the RMM of the nickel, and this is the mass of nickel. Another example, an aqueous solution of copper 2 nitrate was electrolyzed using a current of 1.5 ampere for 60 minutes at 25 degrees Celsius and 1 atm. Calculate the mass of copper metal deposited at the cathode. So this is the molar mass of the copper. So the solution Q is equal to the IT, the current, multiplied by the time in second, and this is the charge for the columns, units. So this is the Faraday's constant, convert to the Faraday's constant, meaning that 96,500 coulombs is equal to the 1 Faraday's constant. So this is the coulombs. So how many Faradays? So this one. So the Q here you divide by the Faradays. For the half equation at cathodes, you get the copper to iron gain 2 electrons. So this is the number of mole, 2. So look at here, the columns, meaning that this one 5.6 exponential negative 2 divided by 2, and you get the number mole of copper. So to get the mass, number of mole you times or multiply by molar mass of copper. And this is the mass of copper. Another example, how long must a current of 0.8 ampere flow to form 2.5 gram of silver metal in an electroplating experiment? The cathode reaction is, this is the silver, gain 1 electron to form the silver in the solid, meaning that the silver metal. And look at this, mass, reactants or product. So look at this, 2.5 gram of silver metal. You need to convert to the mole. So to convert to the mole, Mass you divide by RMM, molar mass. Molar mass of the silver, and you get the mole. After you get the mole, to find the Faradays, so look, 1 mole reactant divide by number of mole of electrons. So 1 electrons here. So this is the Faradays, meaning that is equal to the 96,500 coulombs, and this is the amperes multiplied by time. And we look at this solution. Calculate mole of electrons. This is the number of mole. Calculate quantity of charge. So you get the charge here. So this is the Faraday's constant. So you know you divide by the 1 mole, n. This is the n, 1, because of 1 electron here. And this is the Faraday's constant. You multiply by Faraday's constant, 96,500 coulombs, and then calculate time required, charge divided by current, and this one you convert to the minutes. So the answer for time in minutes, or your answer in second also acceptable, depends on the question. This is the application of electrolysis, electro-refining of metals, purifying metals such as copper, ultra pure copper sheets. This is the cathodes, lower between slabs of impure copper is anodes, aqueous copper to sulfate electrolyte solution, 4 weeks for anodes to dissolve, and pure copper to plate onto cathodes. So this is the refining copper. Look at cathode. Pure copper is deposited on the cathode, and for anode, copper and metals more easily oxidized than copper are oxidized here and enter the solution as ions. This is the impure copper. This is the sludge containing silver, gold, and platinum. And this is the electrolyte, copper to sulfide. This is the electroplating of chromium onto iron. The electrolyte is an aqueous solution of chromium 3 chloride. So this is the equation. Anode, chromium dissolved to form chromium 3 ions. Cathode, chromium gets deposited onto the surface of the iron object. So this is the electroplating. Look at anode. This is the chromium, and this is the cathode for the iron object. And we look at the cathode, the chromium gets deposited, and for the anode, chromium dissolved to form chromium 3 ions. Corrosion of iron, still mostly iron trioxide coating not impervious to further corrosion. Physical stress points leave strain in metal, more susceptible to corrosion. Creates anodic and cathodic regions. Electrochemical process. This is the anode region, and electrons flow through steel to cathode region. So this is the cathode region. This is the manufacture of chlorine, hydrogen, and sodium hydroxide. By chloralkali process, chlorine used in plastic industry, water treatment, sodium hydroxide used in making paper, detergent, and textiles. Brine enters the left compartment where chloride ions are oxidized at anode to produce chlorine gas. At cathode, electrolysis of water will produce hydrogen gas. Unreacted sodium ions diffuse through permeable plastic membrane to right compartment and react with hydroxide ions to form sodium hydroxide solution. We done the chapter 4 electrochemistry, and we will continue chapter 5 in the next video. And thank you so much.